I am Subhadip Ghosh, a doctoral student in Indian Institute of Technology, Dhanbad, and I am working under Professor Ritik Mondal in his ultra-fast terahertz spintronics group. Today, my topic is anisotropic effect of inertial dynamics and the influence of inter-sublattice coupling on the antiferromagnets. So, first, I will start from what is spin dynamics. When we put a electronic spin in a uniform magnetic field, it will precise around the field direction. So in terms of torque equation, we have an equation of motion, which is like this, where H is a applied magnetic field or effective magnetic field, and M is the magnetization. Uh, Now, if the spin is not in a uniform field, instead of it is in a inhomogeneous field, so there is an inward torque applying on the magnet spin, and it will orient the spin in the field direction. So this term m cross dmdt is the inward torque, and it is known as damping torque. And including this damping torque, we have an equation of motion for spin dynamics, where the second term is the Gilbert damping, and alpha is Gilbert damping constant. So now the question arises: what is the importance to study the dynamics of spin? So we know today in today's world, all the storage devices are made of magnetic materials, and they working on the principle of spin switching. Um, so our data projection by International Data Council shows that in 2025, there will be a huge data generated by overall world, which is 175 zettabyte. It may be more than that, but not less than that. So this huge amount of data we have to store in magnetic devices, and this spin switching technique, the effective time it takes to switch a spin is in the nanosecond order, but in this to store this amount of data, we need some alternative approach to store the data faster and process the data. So in this case, inertia of spin can be helpful. There is a similarity between classical torque motion and the spin motion. So in classical torque motion, our energy equation is this, where the second term is the damping term, and if we consider classical spin as a classical object, so the vector here mentioned, uh, so this vector in classical torque motion, there is a precisional frequency which is phi dot, and this vector itself precises about around it, so which frequency is mu. And this new dot frequency come from the inertial effect. Uh, but in the equation there is no trace of inertia, because when Gilbert derived the equation from classical mechanics, he took the principal moment of inertia I1 and I2 to be zero. But in the real case, this condition cannot satisfy. So in recent work, the scientists take I1 and I2 non-zero, and they came up with another equation which is known as inertial Landau-Lipschitz-Gilbert equation, where this term includes the inertial effect, and eta here is the inertial relaxation time. So in this field, so now where the actual source of the uh, inertia, where the actual source come in the spin dynamics. So when we apply very high frequency magnetic field in the terahertz region, the magnetic moment and the spin magnetic moment and the spin magnetic momentum and magnetic moment cannot follow each other. So there is an effective lagging between them, and for this reason, the magnetization vector will precise about the magnetic moment, which produce a spin nutation motion. This is the inertial effect in the spins. So including the inertia and the precisional motion, we get this type of motion for a spin where m cross b is my precisional torque and m cross double derivative of l is the nutational torque. So another interesting phenomena can be observed here, that the interaction between exchange and the anisotropy will enhance certain inertial effect like effective damping, resonance frequency, and dissipated power. The spin nutation motion is already experimentally verified in nickel iron and cobalt iron boron systems. You can find this from this reference. So my work is based on some mathematical formulation. So I take the inertial Landau-Lipschitz-Gilbert equation, and to counter the anisotropy, I take the eta as tensor, which mentioned here by D, and I split the tensor into two parts, symmetric and antisymmetric part, writing this antisymmetric and symmetric part in this way, where Ij is the symmetric tensor and I and J are the two sublattice for antiferromagnets. Replacing the antisymmetric part in the main equation, we get the inertial Landau-Lipschitz equation in form of inertia, inter-sublattice inertia, which is mentioned by in eta I, and intra-sublattice inertia by eta I, and inter-sublattice inertia by eta prime ij. Now I calculate. So we already know the ferromagnetic free energy. So from this expression, I calculate the H effective here by using this formula. And within the linear response theory, I have the two sublattice susceptibility tensor, where already I mentioned that IXY and IXX are the element of symmetric inertia tensor, and I consider here IXX equals to IYY. And here omega is the frequency of respective motion, and other symbols have their usual meaning. Alpha is the damping constant. So into the result part, I found that the frequency response is quite interesting. Due to the introduction of the inertia, the precisional frequency of the antiferromagnetic sublattices goes into terahertz region. And there is another pair of frequency which are known as nutation frequency. They are also in terahertz region, and there is a effective enhancement of the damping, effective damping for precisional motion. As you can see, I took a damping constant 0.05 and it is enhanced to 0.25 for this case, and it going to decrease with increasing eta. Next, I want to show the tensorial effect of the tensorial relaxation time effect, which represented as D, and I took D in Z direction, and D0 is the magnitude. So in this case, we also find that the two pair of frequency, that is, this one is nutation frequency and this one are precisional frequency. For different sublattice, there are two different precisional frequency, which are decreasing. And here interesting is the effective damping is increasing from 0.05 to several order of magnitude. So now the effect, there is another effect due to the symmetric tensor component IXX. So here we find a similar response for the frequency response, but effective damping here is decreasing. Here I will not show the IYY response, because as we know that the octagonal element contribution for the inertia tensor is very small. So that reason I will not include in this talk. Another interesting effect comes from inter-sublattice coupling, which is the effect due to a particular inertial motion of a sublattice in the presence of another sublattice. So here we can see that the mutation frequencies are decreasing with increasing inter-sublattice coupling, and the precisional frequency are further increasing into terahertz region. And another finding for effective damping is that precisional damping is increased, but the nucleation damping is almost constant. So now I will show the effect of this anisotropic inertia and the sublattice coupling on the dissipated energy, which is quite similar to the response of susceptibility. So here with frequency, I plot the dissipated energy, and as you can see, the when there is no nutation motion, that is eta zero and eta prime is zero, there are no no nutational frequency at all. You have a flat line here marked by orange, and there is a small precision peak appear here, which can be clear in the zoom picture. So this one is the precisional frequency, precisional resonance frequency rather. So it appears, but when we introduce the inertia into the sublattice, then there are two additional peaks which are known as nutation resonance frequencies. And you can see that motion somehow suppress the precisional motion, and it goes to a lower frequency side. So it moves from close to zero point 0.3 to 0.2 terahertz. Another interesting thing, when I introduce the inter-sublattice coupling, there is a shift in these two peaks. So in case of nutation motion, the peak is redshifted, and for the precisional motion, the peaks are blue shifted, which are marked by the violet lines. Another result, including the anisotropy of the system, which marked as D0. So when there is no D0, you can find the nutation peaks here. And as soon as I introduce D0, there is an effective change in the dissipated energy. But there is no serious change in precision because my d value is very small. If I increase the d value, it should have a shift in precisional frequency also. So the main highlights of this work are due to the inertial effect, the precisional frequency is reached to a terahertz region, which is a lot faster than normal precisional motion. And effective damping is enhanced due to the exchange and anisotropic interaction between the antiferromagnet sublattice. Effective damping increases with the anisotropic tensor D, anisotropic inertial tensor D. Precisional frequency and nutational frequency, precisional frequency increased and nutation frequency decreased due to the inter-sublattice coupling. And there are in the susceptibility response, the resonance frequencies are red shifted for nutation motion and blue shifted for precisional motion. And also there is a finding that shows that the nutation motion somehow you can see here the nutation motion somehow suppress the precisional motion here, and the we can also term the d as a chiral inertial relaxation time, and in this case, the dissipation power will be enhanced due to the introduction of relaxation time. So with this, I will thank the organizers, and that's all.
Okay, thank you. Does anyone have any short question for this report? Okay, I think